Right, today's topic is a review of describing data. It's chapters 1 through 4 that we covered at the beginning of the year. It was basically a 2-week chapter, so there's really only so much that I can go over with you when it comes to this particular material. So if you identify anything that you feel like you have holes in, go back to that particular section in Canvas. All the PowerPoints are there, all the videos are there, and you can get yourself up to speed with whatever topics you feel like you need to look over. So we start out with variables, and we have two kinds. Categorical, this is where we're looking at sort of like aspects where, you know, we could look at eye color, for example, and say we had 30 kids in our room, maybe 20 of them have brown eyes, 5 of them have blue eyes, 5 of them have green eyes, you know, that kind of thing, where we just kind of assign a count to whatever category we're interested in. So that would be your categorical data. Quantitative, this is things that we typically measure, things like, reading time. Say I'm trying to implement a new reading instructional program for 3rd graders, and let's just say that the smallest amount that they read is 5 minutes, and the most it takes them to read a chapter is 12 minutes. That would be a measurement that I would be taking. Other examples would be income, height, weight, speed in a race, scores on a test. That would be your examples for quantitative variables. Now, quantitative variables break down into 2 different kinds. Discrete, these are if you have isolated points on a number line. Say we just measure people in the class by age in years. I might have a 15-year-old, some 16-year-olds, a bunch of 17-year-olds, maybe a few 18-year-olds. I would have nothing in between. So that would be discrete. Continuous would be something that you would have to measure. So that would go back to that example I used in the previous slide for reading times to read a chapter. I could have anywhere from 5 to 12 minutes, and it could be 2.5 or 3 3/4. So I could have any value in an interval on a number line, as opposed to discrete, which all of the counts show up at the integer values, right? So discrete are countable and continuous are measured. All right, here's a quick summary for how variables break down. Of course, categorical and quantitative. There is a third little category that goes into that initial breakdown, and that would be identifiers, things like social security numbers, driver's license numbers, room numbers. These are just numbers that don't have any meaningful magnitude. You know, like my room number 2216 is no greater than 2213 as far as magnitude goes. It's not less than my neighbor 2217. It's just a way to distinguish the rooms. And of course, quantitative breaks down into discrete and continuous. All right, so representing categorical data, we can do these mainly in table forms. For a single variable like shipping method, you can just break it down into subcategories, ground, second day, and overnight, and take the total number of purchases and just break them down by those 3 breakdowns. We could have contingency tables, and these are tables that we used a lot throughout the year. This is where we have an interaction of 2 categorical variables, in this case, survival on the Titanic. We had the class of the people on board. We had whether they lived or died. The inner part of this presentation was the data, this table, and we had the labels and everything. We had these subtotals, which in this case along the bottom, we would call that the marginal total for the class on board the ship. And then we had these 2 values, which we had as a marginal total for whether or not people survived. We had a grand total. So we could work out, you know, things within the margins. We can even go drill down deeper and look at things that were, what's the word I'm trying to think of? Conditional. So I could restrict my view to just third class passengers. And so if I was interested in how many of them lived, it would be 178. If I wanted the probability of living or the proportion, it would be 178 out of 706. So a lot of things we could do with this. We used them all year. You may recall we used them for chi-square. We were looking for differences in proportions or independence. Even early on, we looked for a relationship, and we kind of figured out that, you know, if you're in the first or second class, you had a survival rate that was typically higher than if you were in a third class or if you were a member of the crew. So there's your lack of independence and all those things that we covered. In quantitative data, we're just concerned with just getting numbers of things. For example, here we have numbers of AP exams. That's just a single category, and we're just looking at, you know, how many of them had 0, how many of them had 1. So we had 0 at a frequency of 1, we had 1 at a frequency of 1, we had 2 at a frequency of 1, we had 4 at a frequency of 2, and so on. So there's your representation for quantitative. This is a frequency distribution. That's what we called it. All right, so the graphs that we studied for categorical, we had bar graphs, we had segmented bar graphs, and we had pie charts. We could do them either singly or we could do them comparatively. So we could have more than one pie chart. We could do a breakdown of education level with one pie chart for young people, another pie chart for older people. We could have 2 segmented bar graphs in the same graph. We could have multiple bar graphs in the same graph. So either single or comparative. For quantitative, we had dot plots, stem plots, histograms, box plots, and ogives. Now, ogives were very useful. They were interesting. I really don't think we'll see them on the AP exam. In fact, in all my time doing this, I've only ever seen anything remotely like an ogive one time. It was years and years ago. So I don't think I'd spend a whole lot of time on this. Now, we can have them singly or, again, comparatively. You could have more than one box plot in a graphical display. We could have side-by-side stem plots. We can even have more than one histogram, you know, where we're doing it in a comparative sense. We could have more than one dot plot. One thing is, in this presentation, I am not reviewing how these things are constructed. You can go back and look at that if you want to, but I think what we need to do is not to plan to make any graphs on this particular exam, especially since it's only 45 minutes, but expect to get a graph and plan to be able to interpret it. And we'll go into some of the things that we would do to interpret here in a sec. So when we describe quantitative data, we might start with shape. Symmetric, the 2 that we had that were symmetric were uniform or mound-shaped. You can say bell-shaped for that. I would probably avoid the normal because normal is not so much a shape as it is a condition. So yeah, we had skewed. Remember, skewed to the right had the slide going off to the right. Skewed to the left had a slide going off to the left. And we had bimodal. This is where you have, well, in this case, 2 different peaks within the same graph. That usually indicates that you have more than one population mixed together. And then to describe further, we went ahead and discussed, you know, this where we thought the center of our distribution was, any unusual characteristics, gaps, clusters, or outliers, shape, which we just talked about, and spread. All right, and we use the acronym CUS to remember those 4 things. So if you are asked to describe a distribution or a graph, then remember CUS and refer to these 4 items in context, always in context. We had some comparisons with mean and median. Remember, if your mean is greater than your median, that indicates your distribution will be skewed to the right. If your mean and your median are roughly the same, that indicates that your mean and median come from a distribution that's symmetric. And if your mean is less than your median, that's an indication that your distribution is skewed to the left. Good thing to remember. That shows up a lot. All right, so I'm starting out with summary values for any distribution, any of them, right? Because we have this issue of resistance, and some of our measures like mean and standard deviation and range were non-resistant to extremes. So some distributions have extremes. So what might work for any distributions, whether they have extremes or not? That would be starting out with your 5-number summary, and you get that from one variable stats in your calculator, and you get the minimum, Q1, median, Q3, and max. Measure of spread for any distribution would be IQR, Q3 minus Q1, which reminds me, I don't have it listed, but we also had range as a measure of spread. That was maximum minus minimum. Although we didn't use it very often, it wasn't a great measure due to its non-resistance to outliers. The measure of center of choice in any particular distribution would be the median, as it's non-resistant, just like your IQR is. The graph of choice was a box plot, and remember, it was constructed from your minimum, Q1, median, Q3, and max. And you can modify it to show outliers, so it's a really good graph. But keep more on box plots. It is again based on the 5-number summary, and it's especially useful when drawing comparisons because each section that you have represents 25% of your data. We'll see more of that in a minute. We can generate outliers from doing this graphically. If you have your raw data and you graph a box plot using your calculator, it'll just reveal the outliers. Now, box plots don't show shape. Remember, we had that issue when we had to verify normality for statistical inference. But we went ahead and said, you know what? The AP people said it was fine. It will show skew, but it won't show whether things are normal. All right, revealing outliers. These are values that are not in the overall pattern of the data. They kind of are out by themselves. You see them that way in a modified box plot. And it's any value that is more extreme than 1.5 times your IQR in either direction. So if you don't have your raw data, let's just say you have the 5-number summary and you're interested to know whether the minimum or the maximum would be an outlier, you would do Q1 minus 1.5 times the IQR to reveal a low end or a left side outlier. Q3 plus 1.5 times the IQR would reveal one on the high end if there's one present. These you ought to know. These two formulas, I've seen them a lot on AP exams. So when do we use the mean or the median? If you have a bell-shaped distribution or possibly even one that's uniform, remember symmetric, your mean and your standard deviation would be good because you don't have any extremes, you wouldn't have any skews, no outliers. Mean and standard deviation is your best choice. Remember, your mean is the balance point. So if you have a histogram and you can just sort of imagine where a fulcrum might be to balance that thing, that would be a good estimate for where your mean is. And remember, your mean is just your arithmetic average and it is non-resistant to extremes. Along with your mean is standard deviation, and that just measures the average of the spread of your data about the mean, and it is also non-resistant. All right, otherwise with skewed distributions or distributions with outliers, we want the median and the IQR because of its non-resistance. I'm sorry, I guess that would be resistance to outliers. Got to get that right. All right, so your comparative graphs, Again, these are available for both quantitative or categorical if you need to make comparisons. For quantitative, typically you see those more than categorical, and you will see an occasional side-by-side stem plot, but in general, your comparative graph of choice would be box plots, and we had this in our particular packet when we learned it. This was a comparison of home runs made by Babe Ruth and Roger Maris. And Roger Maris did have the most in a single season at 61. Babe Ruth was 60. But remember, this would be minimum, Q1, median, Q3, and max. And between your Q3 and your max is 25% of his highest, of his home run years, which would be his highest ones. From median to Q3 would represent 25% more, from Q1 to median 25%, and from minimum to Q1 would be the final 25%. So that's particularly good for comparisons. So if you look at this line right here that kind of separates, not so much Maris from Ruth, but gives you a point of reference, you could say that if you use this line as a kind of a break, that below that would be 75% of Maris's years, and they would be on the low end, and above it would be 75% of Ruth's years, and that would be his best years. So 75% of Ruth's best years occur right at or above 75% of Maris's worst years. So Ruth is a better home run hitter. That was the point. So that's the kind of method to go about analyzing a comparison between two box plots, is to use how these things are broken down into quartiles to draw comparisons. So there we go.